These are first review problems. It looks familiar, right? Oh, so you searched back in your week 6 notes. Well, yeah, no, that's good to practice. Not, yeah, trying to approach the problem with fresh eyes. The main trouble with these is the rotational to translational. We have two translational elements, K1 and K2, connected to a rotating body. So I did draw this up here for a reason. This is small angle approximation, and the importance of this is we can find, I could label this the end right here as theta increases is going to move upward. And we can basically make a small triangle out of there. I can call that side x1. I can call this side x2. Because it is going to move somewhat linearly at small angles. My question to you is, what is x1 equal to? Because I don't want this in my final equation. Everything should be in terms of theta. So what is x1 equal to for small angles? Yes, x1 is equal to L1. Now, technically, it's L1 sine theta, but because we're using small angle approximation, sine theta just becomes theta. So that is L1 sine theta. That means that x2 is equal to L2 times theta. And that's really important for us because we're going to be using sum of torques equals J theta double dot. But for this FK1, this spring has two ends that can move. So K1, we need a delta. K2, we don't need one. It's fixed to a wall. So it'll just be seeing that L2 theta. But this is going to be the difference. So one of them for the spring is X sub C, that is the cam follower. And the other one is what we just talked about. As it moves up or down, that's going to be L1 times theta. I just want to point out that maybe you have these and they're flipped. That's totally fine. Anytime I have a delta, I can have one in front of the other. I just need to, on my diagram, make sure that, if I'm saying that XC is greater than L1 theta, that means it's going to be pushing up on the body. So I'm going to have my force pointed up. If I have it flipped, I can have the force pointed the other way. But we should have three different torques, essentially. And I'll talk about that on the next slide. But you should have something like this. You can do a similar thing for K2. It just doesn't have a delta. The pivot friction is just going to be a torque. So that's just directly related to theta dot as that thing's spinning. So I'm going to give you some more time to work on this. Our goal is to get to the mathematical model, get to the transfer function, then find DC gain. Yeah. Whoa. Okay, cool. This is the return spring, K2. So that would be FK2. So yeah, for the SSR, it's chosen three things we want to find. So you're going to want to use your definition. Yeah. It is. Yeah, but it's okay. We can basically set any output for the SSR, and so we can actually be tracking an input as well. So we got three sensors. Mhm. This is this, the fourth step. So is that. Those are just linear vertical forces. So we have to turn those into torques. Force times something equals torque. Those things. How are you doing? Yeah, very good. So yeah, TK is equal to force times length. And then we can put all those definitions together. Christian, how are you doing? I believe this isn't square. Yeah, because this is our definition. So then we take this force multiplied by L1 to get a torque. So that would just be 1 L1. Yeah. Yeah. So just on the right side. Our goal is to find transfer function. Yeah, a single input, single output. You can find the DC gain just in terms of variables at this point. And then the goal is to work on the SSR. So I'm going to turn my page. Here's kind of how I did it. We already kind of talked about this, but the main thing is, since this is some of the torques, it is rotational. Notice once I define these, that's not good how it is. That's just a linear force. So to turn them into torques, we have to take the spring force times the distance, or the moment arm. Force times distance gives me torque. Then from there, we can put it all together. Yeah. And this is my All right, so phase one is over. This should be our final mathematical model. I did put some values here. We can find our transfer function. We can do that with variables. If I want to find the DC gain, we can have variables. We can also plug in values to find what that number is. Tell me again, class, what is the purpose of the DC gain? What does it tell us? Related to the steady state output, yes. How do we use it to find the steady state output? Okay, so you plug S is turned into 0. So DC gain is the gain, it's the multiplier at steady state. So we take the DC gain times the steady state input, and that will give us our final steady state output value. It's just a multiplier. So if I double my input, I double my output, right? Because the DC gain does not change. But we'll find the SSR in terms of variables, not numbers. I like it in terms of variables because just like with lab 2, set up your very valuable. If you have any questions, please let me know. If you're not quite sure why yours doesn't match up. All right, stage 2 is complete. That was a little bit easier. I want you to start working on the SSR if you haven't. Transfer function, we just do output over input. It looks something like this. If I want to find the DC gain, that's where all the S's equals 0. There's no more derivatives, there's no more change. This is our multiplier. If I plug in these numbers, I should get 20, which means that theta steady state is going to be equal to 20 times whatever that step input is. That will be our, so DC gain only works with a step or a constant input, just like DC voltage, just to not change it. Constant. All right, I'd like you to transition to, if you haven't yet, the SSR. So taking this in terms of variables, creating the SSR, and for the second part, the output equation, we have some outputs that the problem specifies, and trying to find all four matrices. What is the order of the system again? Second order. So we should have an x1 and an x2. And an input, u. So from there, creating our equation. Do you have any questions? Please let me know. Sorry. How many of you are almost done with the SSR? You done? Okay. Some people are. So the first step is, what's the order? Second order. So I have two x's, x1, x2. We're gonna start with the lowest order. So that's theta and then theta dot. We're not gonna do theta double dot here because we're gonna get to that when we take the derivative of each of those two terms. So right now it's just renaming to rearrange. So we have one input, so u is equal to x sub c. And then we take the derivative of each x, each output variable. So x1 dot is just equal to x2, easy. x2 dot is equal to theta double dot. That's where we take this equation and rearrange it to solve for theta double dot, and then put it in terms of our variable. So once we have that, the first part of the SSR is taking those two equations and setting up our A and B matrix. So derivatives on the left-hand side. This is my A matrix. My vector is x1, x2. Then I have a u vector right here. So we just have one u. So the A matrix, I'm now using those equations. X1 dot is equal to 1 times x2. X2 dot is equal to, well, I've got all of this. I've got this term. This is negative. I have a negative term here. And then lastly, we also have an input term like that. All three of them should be divided by J, moment of inertia. How many of you got to this, at least the first part done? right? Okay. So yeah, based on the order, all the rows of the matrices are going to have the same number as whatever the order is for this first one. So it's second order, I have 2 rows, 2 rows, 2 rows for all 3 of those those 2 matrices. Okay, let's talk about the output. The output equation is all based on what it was calling for. So it called for 3 sensors, one on theta, one on the return spring, which is FK2, that force, and then one on the input, X sub C. So to use those 3, first we need to put them in terms of these new names that we're using. So X1, X2, U. So if Y1 is equal to theta, that's what they want. I'm not just making this up, it's based on the problem. So my first output is equal to theta, that's just equal to X1. The second one, they wanted the return spring force, that's FK2. We have a definition earlier, K2 L2 theta. Theta again is X1. So we can now put that in terms of our new name, X1. And lastly, our other sensor that we care about monitoring is the cam displacement, which is equal to U. So now I've got 3 definitions in terms of my state variables. And we can set up our C and D matrix. So we're going to use the same vectors as before, the X vector, state vector, and the input vector. But I have 3 outputs that we're looking at. So Y1 is equal to 1 times X1. Y2 is equal to K2 L2 times X1. Then lastly, our third sensor is just the input 1 times U. So we got 0, 0, 1 for that equation. So if you're not feeling comfortable about this, I would go back to, I think it was week 7 is when we first introduced this. We have been doing it on homework 4. You probably did it on the lab. But just remembering, you can go back in the slides, start with the problem, not jump through to the end, right? But work on that problem. We've done quite a few examples in class, and so trying to feel comfortable. I know a lot of people get hung up on how do I put this second part together. It's all based on what the problem's asking. You just have to put it in terms of the same state variables you've been working with. It has the same vectors. You just have to figure out how to set up the C and the D matrix using those vectors. Question. We got one last step, then we can take a break. So the last step is up at the top. We want to find the dynamic response. Theta is a function of time. If the rocker arm is initially at rest with an angular position of 0.1 radians, and the input is a step of 2. Or should we take a break now and come back and finish this after the break? You need a brain break? Just go power through, and then we'll do another problem after. Sounds good. So first off, what is the dynamic response? The output response. Theta is a function of time. We actually want to find the exact function based on the given input. We have the values here and everything. See if I've got something on this. Now, it says it's initially at rest, but it has a starting point that is not zero. It starts at 0.1 radians. What does this tell us we need to do? I have to do formal Laplace transform because we have an initial condition. So based on the initial condition, we're going to have to incorporate that. First would be finding the equation, and then following the steps that we've talked about over the last couple of weeks. So you want to plug those numbers in to the equation we have, that number. I like these numbers. We have to be able to solve the Laplace transform. Hey, like we talked about, we've got to use Laplace transforms because we have an initial condition. I can't use the transfer function. I'm trying to find the complete response. What is that actual function? So it tells us it's initially at rest. That tells us that theta dot, the velocity, should be equal to 0 at time 0. But we do have theta at time 0 is 0.1 radians. The input is a step function of 2. So first, plugging in the values, this is what I had for the model. You want to first put it into standard form. And then if I plug in, my step is 2. What is that, 2 meters? That's kind of crazy. But maybe not. I don't know. Maybe the scale of this thing is immense. Anyways, we're doing a step of 2. And so my equation in standard form is theta double dot plus 4 theta dot plus 0.1 theta is equal to 4. Now, wait a second. Didn't we find the DC gain? What is the DC gain? 20. So what's our final value going to be for theta? Twenty times the input, and the input is that's not 4. 2. So 20 times 2 is 40. So we know that our final theta in radians should be 40. Now that might not make total sense. I did just kind of make these numbers up. But when I get to my final answer, we should be able to check as time goes on, are we left with 40? Because I know what my DC gain is from the system. I know what my step of 2 is. And that's one way we can kind of double check this. So the first step is to do a Laplace transform of each of these terms. They involve this initial condition. And then from there, you're going to plug it all back together and solve for theta in the S domain. After that, you look at the roots, partial fractions, we can bring it back to the time domain. And then we will take a break and do some more review. Any questions you having right now? Yeah. Yes. Well, sort of. The problem said it's initially at rest, which means velocity is 0. Yeah. We're not guessing. Any other questions? They're going to do Laplace of theta dot. Oh, sorry, theta dot. Laplace of theta dot. Those both used. This is the Laplace transform of 4. 4 over x. Yeah. So, if you want to pull it Hopefully this is still pretty fresh to you. You just turned in homework 5. Um, hopefully you feel pretty competent with doing this differentiation, combining. Obviously there's some algebra involved, but getting to a place where we can then use partial fraction. So I've got all my Laplace transforms up here. Remember, one thing that really gets people a lot of times is the 4. So the 4 should be, everything's multiplied by 4 when I take Laplace transform of 4 theta dot. And then we plug them all back into the equation. We combine all the thetas together, get everything else to the other side, get a common denominator, and then we can solve for theta as a function of s. So that's our goal, is to, after doing this, combining it to get to here. Once I get there, then I can figure out the roots. I can look at partial fractions and solve that. So, you can, I don't know how far you got, but hopefully you're getting close. Maybe you messed up a few things, but now from here, once I've got theta, now I'm looking at the roots. I'm looking at, okay, what fractions am I going to set up? We are in standard form. That was what we did first. That's good. I don't have to, I'm just going to match the table, find the constants, and then bring it back to the time domain. Then we'll take a break. Any questions? It's good. Charging your calculator. Pre-charge, ready for Thursday. Oh, wow. Oof. Mhm. Anybody find the roots? Well, I know one of them is 0. The other two. You found the other two? Yeah, that's correct. Yes. Yep. Yeah, it's like negative 0.025 and negative 3.97. Yeah, yeah. Uh, I think it's fine. So hit next. That button. Yeah. Mhm, 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 mhm. What? What are they? 0, negative 3.97, and negative 0.025. They're two negative real roots. So if I have negative real roots, that means I just have an A term, and they're not repeated. That would be line 7. So I'm going to actually set up 2 of line 6, one with each of those roots. And then I'm going to have line 3, because I have a 0 root, s equals 0. So we're going to have 1 line 3, that's one partial fraction, and 2 line 6s with those other uh, real roots. Again, roots are negative a plus or minus omega I. In this case, I don't have any complex roots, so we just have an a term, basically. So it's going to look something like this. Right. I know my partial fraction. Now, our goal is to find these. Once I find these, it'd be real easy for that instead of just like this. Once I have that constant, I go with it. So A is going to be constant. And then we got this. We're going to find a B and a C value. We just want to make sure that we have all common denominators. So I have to multiply A by what's missing from the denominator, B and C. So from there, we should be able to solve. Well, like I said, our goal is to find these three constants, but I need to have a same common denominator. A is missing that whole polynomial. So we're going to multiply A by the polynomial. To match the same denominator, B has to be multiplied by S and the other part of the root, which is S plus 0.025. And then similar for C. So you just want to make sure that when you're solving this, yeah, we set up the partial fractions based on the table, based on the roots. But after that, we're going to get a common denominator. Now I can actually go ahead and solve this using my polysymbol 2. Some of you are just learning about this today. Real helpful. We can find the roots with that. We can also solve a simultaneous equation. Yes. So for example, I can, get all my S squares together. So we're looking at A, B, and C. Now on your calculator is probably X, Y, and Z. But once you have all those set up, we should be able to solve. And guess what? I was right. A is equal to 40. Isn't that crazy? Because we knew that the DC gain was 20. We knew that the input was 2. So 2 times 20 is equal to 40. That's what we should end up at. That's our steady state value. Yeah? Oh, you messed up somewhere? Yeah, it's easy. Does this match up? Oh, you're good. Now you could have set them up a different order. It's fine. Okay, it might be a decimal. Oh, yeah, maybe. Um, that's weird. Yeah, there's. I probably could have been a little bit better with the decimals here because A plus B. Oh no, that makes sense. So we're using calculators to solve this. Now we find the three terms, and it's really easy from here. I know it was hard setting it up. Solving for theta, that's difficult. The roots shouldn't be too difficult, but then it's setting up the partial fractions. Then I got to make sure same common denominator, and then set up this system of equations. We can use our calculator to solve this. And now we're at this point. This is the easy part. I know what these relate to. I have a table. I'm just going to bring them back to the time domain. So therefore, theta as a function of time is equal to 40 plus, this is my B value, 0.3 e to that. So that's going to die out after about a second. And then we've got this, and this dies out after quite a few seconds. But we can, again, check a few things. We know the DC gain was 20. So this makes sense. 40 should be our final value. We can also double check theta at time 0. That should equal 0.1, and it does. So that is how we can solve for the complete or dynamic response of our system based on a given input without initial conditions. If I had no initial conditions, we could have just used the transfer function. It makes it a little bit faster. But I would still have to do all of this step right here. So change our answer a little bit. Now we had no initial conditions, no starting position. I'd like to take a break. I think we've done quite a bit of work. This was a pretty difficult problem. It's a lot of steps, right? But the reason why we're practicing it is similar to what you may see on the test. So let's take a break. Let's come back at 8:46. That gives us about 45 minutes. We're going to do one last problem together, like a 30-minute kind of problem. And then there's other problems on here that you can do on your own time too. But let's take 5 for now. If you have questions, I'll stick around. Yes. Yeah. Yes. It's crazy. So you're like, when it opens up, you're ideal spot. Nice. That's a lot. Oh no, I don't have my notes. I think it would be good practice, to be honest. Hey everyone, let's take 30 minutes. We're gonna solve this problem, but I need your help. So I don't think I'm gonna give you a whole lot of time. We're gonna go through this together. There are other problems that we will not get to, but I do have some answers posted to some of them, so you can try them out as practice. Let's say that I've run a test or someone's run a test. We've got this graph here. We're just going to look at the solid line, not the dotted line. And we knew that the input was a step of 6 newtons. You know what? No. I'm going to change that to, this usually gives us like satanic numbers. So I'm going to change it to pi newtons. How about we'll just go 8. It'll still be okay. Okay. Let's say the input is 8 newtons. All right. And our goal, now this is an approximation, so it's not necessarily finding, but we want to approximate M, B, and K. So if it's a mechanical system, I give it a step of 8 newtons. We see the system respond like this. We can approximate what M, B, and K are, which can help us run other simulations and all that. So I do need your help. Should I just guess 3 numbers and call it good? So mass is 1. P is 1. K is 1. We're good. Let's move on. What would another method be? Zeta, damping ratio, frequency. Yes. So, how about this? How about this? We have a standard form for second order equations, which looks like y double dot plus 2 zeta natural frequency y dot plus natural frequency squared y equals some kind of constant times the input. So this is a standard form for a second order system. Now, this will not exactly get me M, B, and K, but it'll get me pretty close. Because I should be able to find or approximate the damping ratio. I should be able to approximate the natural frequency as well. So, I don't know. Are we closer? I'm not really sure. You think we're closer? Okay, what's the next step? Mr. My bracket's in the lead. So thanks, ChatGPT. Make a song. Oh, that was all you. Yo, you just put GPT in the name. He is GPT. Oh, yeah. All right. But do you have an answer? What's next? Now, there's a few ways we can go, so it's not like there's one. You want to find theta, and how do we find that? Log decrement. Yeah, great. So log decrement. That's the formula. Now it asks for three things. There's three things we need to put in here: n, x1, and xn. So to use that formula, we've got to figure out these three things. And what would you say n is equal to? Say it again. 3. Sounds good to me. For those of you who may not know, what does the n stand for? Well, it's the number of peaks that we have before we reach steady state. And so we have one peak, that's peak 1. We got 2. We got 3. I think 3 is great. So if we say n is equal to 3, now it's our goal to find, so this would be x1, and this will be x3. So it's going to basically look at how much decay we have from peak to peak. The more peaks we have, the better the approximation is. But x1, what would you say x1 is equal to? Again, this is just as good as you can kind of guesstimate. What? What is it? X1 is 3? Oh, I see. I see where we're. Yeah, this is not based on the seconds. No. This is on the y-axis. Now, the other thing on the equation sheet that it tells you is that this peak is not the absolute value. It's not with respect to 0. It is with respect to the steady state value, which is 1. So x1 should be whatever 1 point. I don't think it's exactly what. I don't know about that, but maybe it's like 1.52 minus 1, which is our steady state. So I would say that x1 is equal to ish 0.52. I don't think it's exactly in the middle, but it's a little bit higher, so that's why I went with 0.52. You can say 0.53, it's not going to change your answer much. Now x3, again, same thing. It is not the absolute value, it's with respect to steady state, which is 1. What would you call that? I like this 0.05. Close enough? Great. Yeah. So it looks like maybe a quarter of the way between there. So, okay, cool. Now we have the log decrement formula. So we're going to plug this in. Now this value, xn, whatever that last one, that should always be small because we should be getting close to steady state. And so that's also a good check for us. So now we have log decrement. So damping ratio is equal to, we have 1 over n minus 1, so that's just 1 over 2. Natural log, we have the 0.52 over 0.05. Then we've got this large square root. This is 4 times pi squared. Plus, again, we have 1 over 2 times natural log 0.52 over 0.05. Can I borrow someone's calculator? I forgot mine. Thank you. Okay. So, you can double check me on this. Um, so much different than a Casio. Anyways, I got the denominator here. I'm not rich enough to have these guys. And this is 1.171. So I got 0.183. Real quick check. Thank you. Does that make sense for a damping ratio? Yeah, it does. We definitely know it's underdamped. It should be less than 1. We do see a pretty sizable peak, so this does make sense. If you get a negative value, that also is an indication you did something wrong. So if it's below 1, you should be go. The higher the peaks are, the smaller the damping ratio is going to be. The next step we want to find is, so the other thing that's a part of that is the natural frequency. Now, on the equation sheet, the natural frequency, I'll get to that. Natural frequency is related to the damped frequency. That's the frequency we see here. From here to here is 1 period. So to find the natural frequency is related to the damped frequency, which is related to the period. So this is the other piece of information we kind of have to figure out. What would you say that period is? Just straight up 6? It's not 7. We know that. Is it 6? I don't know. Maybe 6.5. 6.5 sounds good. Okay, let's say this is 6.5 seconds. What that means is the damped frequency is 2 pi radians over the period. So we have 2 pi over 6.5 seconds. Someone do that for me. I don't have that. No, wait, I have it. I actually have that one. It's 0.967 radians per second. No one on this YouTube's going to understand anything. That is the damped frequency. That's the frequency that we can see here. Obviously, we approximated the period, but the frequency we could say is almost 1 radian per second, because there's 2 pi radians for every cycle. That's what's going on here. Now, on the equation sheet, damped frequency is equal to natural frequency times square root of 1 minus zeta squared. So again, our equation sheet has a bunch of equations where we relate, if it is an underdamped system, we can look at the frequency, settling time, all that stuff. So now we can solve this. So natural frequency, we can just rearrange it, is equal to damped frequency over square root of 1 minus zeta squared. So I've got 0.967 radians per second divided by, this is unitless, it's going to be 1 minus 0.183 squared. And it's going to be slightly larger than the damped frequency. Do you have it? 0.98, bless you, 0.984 radians per second. All right, this is a great starting point. Great, because my standard form equation has those two values. So I find the first one with log decrements the most accurate approximation. You can look at maximum overshoot, you can look at settling time, but those, they have a little bit more uncertainty. Oh my gosh, did I bring that in? Uncertainty, remember that? You take rates? Oh, okay. Uncertainty, wow. Anyways, don't worry about that. But log decrement, a little bit more precise. I know that we are approximating some of those values, but based on the peak, can give you a pretty, I think, the best way to find the damping ratio. Then we can use the period to solve for the natural frequency, which is 0.984. So we've got these two values. We're going to take them to the next slide. We can plug them into our equation, and we get a little bit closer to finding what an approximate MB and K would be. Now, before I turn the page, do we have any questions? Okay, so we got 0.183, 0.984. So damping ratio 0.183, natural frequency 0.984. Let me put that standard form equation up again. So standard form is y double dot plus 2 theta natural frequency y dot plus omega, so natural frequency squared times y equals some kind of constant times our input. Now, we can just plug these values in. So y double dot stays the same. I can get my little calculator out. 2 times 0.183 times 0.984. That gives us this value of 0.360 y dot plus, what is 0.984 squared? That is 0.968 y equals some kind of constant times our input, which is 8. So it looks like mass is equal to 1, B is equal to 0.36, and K is equal to 0.968. Mass is always equal to 1, right? Wait a second. But what is A? 1. Can I just say 1? Done. 1 means done. Done is 1. 1, 1, 1. Lots of fun. Read a lot of Dr. Seuss. But I just made that up. That wasn't actually Dr. Seuss. That was just my, yeah. That's on YouTube now. Yeah, that might be. All right, let's write the equation a different way. M y double dot plus by dot plus k k times y equals my force, which is equal to 8 newtons. So that's our typical, if I have a second order equation for a mechanical system, force is on one side, that's my input. Then we have these three elements affecting the output. These two equal each other. This is the same thing as this, it's just rearranged. How is it rearranged? You tell me. How do I get from here to there? Divided by mass, absolutely. So if we divide this by mass, that gives me my standard form. So this becoming that is if we divide it all left and the right side by the mass. So that means that A is equal to 1 over mass. A is equal to 1 over mass, which we don't know. We don't know B, we don't know K. So we're kind of stuck right now. This term right here is the same as B over M, and this term right here is the same as K over M. So I have 3 unknowns, but I only have really 2 equations that can get me there. So we need something else. Do you remember? You just did the homework. Is there something else that we need to look at? Any ideas? All right. Let's focus on this equation right here. What I'd like to focus on is what happens at steady state, because that's the key right here that we're missing. What happens at steady state to this equation? As everything kind of levels out, we reach a steady state. What happens to acceleration? Goes to 0. Velocity goes to 0. What I'm left with is just k times y steady state is equal to the force. We could also look at this as DC gain, right? So DC gain is just basically 1 over k. That's my DC gain. So we can use it, it's all kind of synonymous here, but we know that y steady state from the graph is just equal to 1. That was in meters. So if this is 1, that means that k is equal to 8 newtons per meter. So another way to write it, DC gain, if I created a transfer function, which you can, DC gain is equal to my transfer function, which would just become 1 over k. So 1 over k, y steady state is just equal to 1 meter, is equal to 1 over k times the input, which is 8. And therefore, that makes k 8 as well. 1 over 8 times 8 equals 1. So a couple ways to go about it, but looking at steady state, this is how we can find our stiffness, our approximate. This could be a very complicated system. We're just creating a very quick approximation for a second order model. If k is equal to 8, now I can take that and plug it into the other ones. Now we can solve for mass and we can solve for B. They're not going to be 1. Right? I mean, I guess it could be 1. But if you're just saying, hey, well, let's just make mass 1, that's probably not right. So I'm going to take that k and we're going to plug it in to here. So K over M, we have 8 newtons per meter over M is equal to 0.968, which is the natural frequency squared. And so therefore we can find the mass. What is 8 divided by 0.968? What is it? 8.26. Thank you. So 8.26 kilograms. Now I can take that and I can plug that in here to solve for B. So B over M, now we know the mass, 8.26 is equal to 0.360. And so we can solve for B, it's just going to be 8.26 times 2.97 Newton seconds per meter. So we have an M, we have a B, and we have a K. Now I can put my equation together. Basically, it would just be this equation right here, but we found an approximation here. I think on the homework, hopefully you did something like this, then you checked it in Simulink, so we can check it when we got our computers, right? I can plug in the same input of 8, and we should see a similar graph to what we did if we did it correctly. So. Questions? You can also, again, the equation sheet has like a whole page using the natural frequency and the damping ratio because it is underdamped. You can double check your settling time. Does that match up with what you see on the graph? So you can plug in a bunch of those different things just to double check, does this make sense? Once I have those values, and then you can do that here. But just make sure there's a difference. We should always put things in standard form when we do Laplace transforms and all that. So after this, I will post these slides. This is a good problem to try. So it's similar to some of the homework that you've done. So if you're looking for practice problems, I would just go through some of these slides. I have the answers up here so you can check it. There's also some of the block diagram stuff, so you understand some of that. I have the answer right here. If you want some more practice on circuits and all that, I have the answer here, so you can take your time and work on this. But for the exam, again, make sure you know how to use your calculator, make sure it's charged, and that if you don't have one that has all those tools, I mean, try to borrow it from someone, but you will have the equation sheet. I also have this problem, which you can also try as a practice as well. So there's some mechanical, there's some electrical, but you can definitely look back at homework 4 and 5. If there was any problems that you didn't quite get to, those are good practices as well. Does anyone have any certain questions, anything that I covered from the beginning that maybe we didn't practice, but you want some explanation on? Subtract from, why did I subtract from 1? Or this? Oh, wait, like all the way back here? So why I subtracted 1 is that for the log decrement formula, the peak needs to be with respect to the steady state value, like where we end up. And so x1 is not the 1.52. It's going to be 1.52 minus the endpoint, which is 0.52. So we're looking at the difference from peak to steady state. And that's what's listed on the equation sheet as well. Other questions? And as you're doing some review problems and stuff, and I do have a lot of office hours today as well, but if you're doing practice problems, yeah, use the equation sheet. Make sure you're really familiar with it too. Any other questions? All right, you can stick around if you got certain questions. If you have anything about the homework, I'll try to grade the homework today so you can get some feedback on it. Yeah, that's my plan. And then Thursday, try to come early and we'll knock at this. What? Yeah, yeah, I think it's good. Test. I mean, similar homework and what we got in the slides and stuff. Yeah. Cool.